Okay, good day, everyone. So welcome back. Now, on Thursday, I went a bit over time, and by a bit, I mean 25 minutes. Wait, it was probably longer than that. No, it was definitely longer than that. And I noticed that everyone patiently stayed for that time. Typically, if I go over time, some people leave, but no one left this time. And the reason that that happened was because I was discussing the midterm after it, and you knew that I was discussing the midterm after that. Well, okay, so these tactics get learnt, and I'm first going to get through some new material, keeping your attention for when I answer questions about the midterm after that. This way, I actually get to get through some new material and still have you paying attention through that, of course. But before that, does anyone have any general questions? So what I'll do at the end of this lecture is that I'll take any questions about the material of the course of this class. So like absolutely anything. It's free for all, open, except you can't ask about homework problems and your solutions to homework problems, but you're allowed to ask about the parts of homework problems that I discussed in lecture. So for example, I discussed unique left, and I discussed how to do the first proof, mostly, in lecture. And we can talk about that as well. How are people feeling for the midterm? Does anyone have any comments?
So is the midterm, so we're allowed to do the midterm for like 24 hours? Or I'm a
40
bit
hours, actually.
40 hours? Yeah. So we're allowed to look at the notes and like our previous homework and that sort of thing, right?
Yes, I'll give a complete list on the midterm, but you are allowed to look at Lackey, my notes, so my notes, Prabhakar's notes, all of the questions on Piazza, but you're not allowed to ask new questions on Piazza during the midterm, all of the emails that I've sent and all correspondence, and all solutions to homework problems. So any
Are you
material that I've shared, you can look at. What's not on the table is that you're not allowed to look up answers to problems or consult other sources in search of answers to problems.
okay? And then are you sending us the midterm after class today?
Yes,
Or
well, I'll send it so the midterm is supposed to start at 8 p.m. New York
got it.
time, and I'll send it to everyone right at the start.
Okay. Thank you.
And then you're still allowed to like use the internet or do all of the things that you would usually do. Just you really do know if you're using the internet to look up things that are related in any way to this course. And if you're doing that for not one of the resources on the whitelist, then that's academic dishonesty and you shouldn't be doing that. Speaking with friends on Facebook is perfectly fine, if so long as it doesn't have to do with this course. What does not have to do with this course mean? Well, I trust that you know. Right? So I don't anticipate that I'll have any problems with this. And one thing that I do want to emphasize is that on the midterm, there will be very significant restrictions on how you're allowed to write problems. For example, for all of the coding problems in the beginning student level, they have to be written with structural recursion. So it's very strict requirement of structural recursion. You will get less than half the points in the question if you, for example, write them with accumulators or other forms of recursion. They have to be structurally recursive. And the other thing is they have to only use functions from a whitelist of language constructs that I give. So Racket has a bunch of built-in functions, but unless I explicitly say they are allowed to use one, you're not. And you might still want to use one, in which case you'd have to implement it yourself. But if you want to implement it yourself, well, that name's already in use. So you just tack on my in front of it, for example, and then implement it yourself. Any questions?
So technically, we can use any sort of functions if we know the definition of them.
Well, I mean, if you can implement them on problems which allow helper functions, right? There are going to be some problems which do not allow you to use any helper functions at all.
Yeah, but technically, I can sort of tuck those definitions within a single definition using.
Yes, exactly.
Yeah, I see. I see. All right. Thank you.
I guess the only really high level abstract restriction which I placed on the homework assignments was that you weren't allowed to solve unique left in terms of unique right by doing reverse. And I said that you can't do anything to the effect of reverse. And then I think I policed that by actually looking through people's homework, but I didn't have marmosets set up to detect whether anyone was doing something which amounted to reverse. That's hard to do. It's also hard to do to check whether someone writes something by structural recursion. So I will go through all of the code manually, not for the sake of giving partial credit when code doesn't work, but for the sake of taking points away if code isn't written in a structurally recursive way. Now, okay, that sounds cruel, but remember, you can test your own code, right? There should be no reason why you think that something works correctly when it does not work correctly, because being able to run the code on some tests is a very efficient mechanism. All of the problems will have a sample input, and at the bare minimum, before submitting, you should ensure that at least it gives the correct output on that input. Okay, so those are some general comments. I'll answer more questions about the midterm after, but first I actually do want to get through some material. Okay, any more questions? Right, so let's start. I'm just going to finish writing the rules that I was just doing before class. Okay, here are the three rules that we have for reasoning. These are the rules of thoughts. These are the rules by which you justify proofs in the implication fragments. Right now, they're written in what I call monodirectional form, and we're going to put them in bidirectional form, which is something that, well, I was supposed to discuss in greater detail before Prabhakar's lecture, but we didn't have time. So I don't consider the bidirectional rules to be something that's been actually explained in full earnest with all the detail that it deserves yet. So that's what we're going to start with today. I mean, after doing some examples just with the monodirectional rules, which are written here.
What does
The
this
monodirectional, go ahead.
what does this like sideways T means? Like
Okay, so that symbol, this is called a turnstile. That's just a name. But what does it mean? So we have this thing called sequence. And the sequence, for example, in context gamma. So gamma is some collection of assumptions that you have. And then we have some type or some logical statement T. And then we have some proof, colon T. So what the sequent actually means is, sorry, what the turnstile actually means is it doesn't necessarily mean something on its own, but when you combine the turnstile with a colon, then this construction is a three-place relation. In other words, we can write statements of this form, and together those mean in context gamma, T is a proof of T. So the meaning of the turnstile and the colon combined mean exactly this statement. when you plug in those three things: a context, a proof term, and a logical statement or a type.
Is
And
there
just to remind, go ahead.
is there a specific reason why you use a turnstile instead of like the traditional arrow we have?
Because it's not an implication. Implication is a type of logical statement. In the contexts, these are assumptions that you've made already. So think about how to prove an implication, for example. To prove an implication, you assume the left-hand side and prove the right-hand side, right?
Mm-hmm.
So once you've assumed the left-hand side, you need a way to keep track of assumptions. And so that's what motivates the existence of contexts.
Okay, got it.
So for example, if you didn't have contexts, then you wouldn't have a way to prove arrows, because how would you assume something? You don't have a place to put your assumptions.
Oh, okay.
So really, that's a good way to explain it. A context is a storage space for assumptions. Any more questions? Okay, and I want to define also what the grammar of the things that we're currently discussing is. So we have really two kinds of things. We have proof terms. So these are called terms, and they should be thought of as the proofs themselves. So what is a term? Well, there are three variants to what a term is, and these are the three variants in the language of lambda calculus. So what are the three variants? Does anyone remember?
Variables, abstractions, and applications.
Yes. So I'm going to write it right now in the notation, which we'll be using in proof terms as we discuss the rules. Proust has a slightly different notation for proof terms. As Prabhakar mentioned, for example, the dot has a special meaning in brackets. So in Proust, it's replaced with a equals to greater than sign arrow. So every single proof that we write in the implication fragments will be some term. And then the other thing that we have is the actual logical statements, which we're trying to prove. And those are known as types. Or you can also say AKA logical formulas. So the key idea in the second half of this class is that there's this way to see proofs as programs. And then there are two perspectives on the material: the programming languages perspective and the logic perspective. In the programming languages perspective, you talk about types of programs, types of pieces of data in the program. So for example, the square function takes numbers to numbers. That Racket doesn't enforce types at compile time. In fact, Racket doesn't even necessarily compile code. But other languages do this. So the contracts were informal things, but you can make them formal. But in the same way that we reason about contracts, we can reason about types. So that's the programming languages perspective. The logic perspective is that these are logical statements involving implications. And so a type is either, well, it's one of two things. What are the two things?
Is it either a logical formula or an implication?
Yes, except for the first one. We call it, it's called differently. No, logical formulas are literally what we're currently defining. We're right now defining logical formulas. So logical formula, the second one is an arrow or an implication. That's right. But what's the first one?
Would you call it a proof term?
No, proof terms are proofs themselves. We're talking about the actual logical statements.
Then I guess I forgot the name.
But what would be an example of such a term? Sorry, of such a expression, of such a type. So
That
like,
could
what's an
be-
arrow, for example? An example of an arrow type.
That would be like an implication, like
So
type T1 implies type T2.
give me an actual concrete example where T1
Oh.
and T2 are some specific things.
T to W. for
Sure.
example.
Let's also say A to B. Or A to A, for example, right? So sort of T and W are meta variables for it. We usually denote the actual variables as letters at the beginning of the alphabets. So A to A, for example, right? That's an arrow, right? Okay, but so what is the other type of type? You have arrows and then you also have,
Like variables, I guess, like single.
yes, they're called propositional variables in this case, but we can also say variables. And those will just denote like as a meta variable A for any propositional variable in the same way that X is a meta variable for any variable. So a type is either a propositional variable or an arrow. I want to So in other words, well, propositional variables, their meaning is outside of logic. A could mean, for example, it is raining outside, but that's outside of the discussion of logic. You just have an infinite amount of variables that you could use in types and an infinite amount of variables that you can use in terms. So we assume that the alphabet goes on forever. Well, you won't need that many in those that you encounter. What I mean by a variable, well, that's sort of outside of the grammar. There's just should be some unambiguous variance that I'm able to recognize as a variable. In Racket, we'll do this with a feature called symbols, but let's ignore that for the moment. So what we have then is that all of our terms are going to be lambda expressions defined by the grammar for terms. And all of our types are going to be type expressions defined by the grammar for types. And we also think of types as logical formulas. And then we have this key thing, which is called the BHK interpretation. So I'll leave the proof rules there and just scroll down enough so that I can write that. And that's really what powers this entire analogy. The BHK interpretation of a proof of, let's say, T1 implies T2, or T implies W, is a function that takes a proof of T and produces a proof of W. So this is perhaps one of the most important points to understand, or at least remember this line. A proof of T implies W is a function that transforms a proof of T into a proof of W. So the meaning of this is, I could say, for example, if I were a millionaire, I would buy a yacht. And I could, in my mind, reason through that. And I could convince myself that that statement is true. Now, I can't convince myself that I should buy a yacht because I'm not a millionaire. But if I were given a proof that I was a millionaire, then I could take that proof and I could plug it into whatever cognitive devices let me conclude that that would imply that I would buy a yacht, and conclude that I should buy a yacht. And in this case, we're actually going to take the interpretation of what a function is very literally. We have a very simple language for describing what functions are. And that's the language of lambda calculus. All that lambda calculus has is function formation, function application, and variables, which are the parameters of functions, parameter names for functions. And then types can either be interpreted as implication statements or saying that a type of a function takes an input of type something, let's say it takes an input of type T and produces an output of type W. And so in light of that, we took rules for reasoning that did not have these annotations of proof terms and put in proof terms beside of the rules. So the first rule says that if we assume X is a proof of T, then it follows that X is a proof of T, right? That sounds reasonable. What was the name of that rule?
Assumption.
That was what we called it when we did not have type annotations. But when we added type annotation, we renamed it to it was var. I'm not sure if I heard that.
No.
Or variable. And the reason that it's called variable is to emphasize the fact that in contexts, all our proof terms are going to be variables. So you won't have a context consists of variable type annotations. So for example, if you're trying to understand the type of the square function, square is lambda x, it takes x, and then it multiplies x with itself. Now, again, multiplication doesn't exist in this logic that we're considering, but we can imagine a programming language analog where it does. In which case, if you're trying to understand what type the function is returning, then if you know that the function takes a number, you assume that the name x now refers to some number, whatever is passed into the function. And then you have that as an assumption that you can use for making other type deductions. So for example, multiplication. What does multiplication produce? Well, multiplication produces a number when it's fed to numbers. And then that's where you actually use the assumption. But again, what I just described is a process of reasoning that's not occurring in what we currently have because we don't have multiplication. All that we have are lambdas. Okay, now what about the second proof rule? So what does the second proof rule say? It says that if in some context where we have a proof of T, which is going to just be called by some name, a single variable name, we're not assuming that some proof term, compound proof term proves T. We're just assuming that some variable stands for a proof of T. Well, if in the context with that assumption, we have a proof little t of W, where the variable x might occur in little t, or it might not, then we can form a proof of T implies W, which is a function that takes a proof of T and returns a proof of W by forming an abstraction. It's a function that takes a single parameter called X, and then it returns the body of X. Well, if you do an application, it'll substitute, but we're not talking about substitution or computation at the moment. All we're saying is that this lambda abstraction is a proof term for implications. And what was this rule called? So it was either implication, introduction, or elimination. Which one was it?
Introduction.
Yes. Does anyone have any questions about that?
Yeah, so if I were reading that entire thing out loud, what would it sound like?
Okay, so if in context gamma, along with the assumption that X is a proof of T, we have that T is a proof of W, then it follows that in context gamma, the term lambda xt is a proof of T implies W.
Thank you very much. I actually never realized that the comma meant along with. So that makes sense.
Yes, right. So gamma itself probably doesn't have an assumption that says T. T might occur twice in gamma, but gamma doesn't need to have T. This means gamma with an extra assumption added to it, which is X has type T. And I'll use the language X has type T or X is a proof of T interchangeably. Any more questions?
So the dot between lambda x and t is not pronounced.
No, it's not, because if you actually think about it, all lambdas in this language only have a single parameter, and that parameter is always just a variable. So it's lambda x, lambda the name of the parameter, and then the body of the lambda.
Okay.
So for abstraction, the first variable that describes the left-hand side, the implication, right?
What do you mean for abstraction? For
The
the
lambda,
grammar term of abstraction or the proof rule?
the proof rule, like in lambda under implication introduction, the x would represent the big T because on the left-hand side, and the little t in the lambda after the dot represents the output of that function.
Yes. Yeah, well, technically the output of the function, the output only makes sense if you evaluate the function, right?
Yes.
And the output would be obtained by substituting, although we're not discussing that right now.
Okay.
But what you're thinking is correct, probably. T is the body of the lambda.
Yeah. Thanks.
So in Racket, for example, again, in brackets, we could write something like lambda x times, this is multiplication, xx. That would be a
Method.
lambda function. So in Racket, this is Racket.
Yeah.
And then the t would be the body of the lambda, which would be this multiplication expression. Notice that x occurs in the body.
Yes. That's how we evaluate.
Okay, any other rules? And remember, this Racket's term, it's in a different syntax from Proust's syntax.
Yeah.
And Proust's syntax is different from the syntax that we're writing right now by a tiny bit. Okay, and then the final rule says, if we have an implication, and we're going to work in the same context, the context doesn't change in this rule. If in the same context gamma, we have that F is a proof of T implies W, and that A is a proof of T, then the application F applied to A is a proof of W. And what was this rule called?
Implication elimination.
Yep. And the programming language's perspective of it is, well, if F is a function that takes something of type T and produces something of type W, and A is something of type T, then F of A should be an output of type W, right? Now, F and A here are metavariables for any proof term. So functions don't have to be variables. In fact, often they're going to be lambdas, for example. And sometimes they might be variables if you, for example, you're assuming an implication. And then assuming an implication would be saying taking an or function as input. But the key to remember is that the reason this analogy makes sense and goes through is because we're sticking to this thing that's underlined in green at the bottom of the screen. The BHK interpretation of a proof of T implies W is a function that takes a proof of T and produces a proof of W. And one thing that's important to emphasize and that people get confused about is that there is a very big difference between the logical statement T and a proof of T. So a logical statement is any type. It's defined by one grammar, whereas a proof of any logical statement is a term defined by the other grammar. And these are two completely different universes. So T implies W is a logical statement. On the other hand, a proof of T implies W is a proof term. And the BHK interpretation says that a proof term for T implies W should be a function that takes a proof of T and produces a proof of W. Now, remember, sometimes variables might denote functions. So the proof doesn't literally have to be a lambda term. It's a term in lambda calculus, but it doesn't have to be an abstraction. You might be working in a context where a variable represents a function. But no matter what, the term that is understood to be a proof of T implies W should be understood as being a function that takes something of type T and produces something of type W. And then you have these three rules. And the key thing about these three rules is that if you look at what the proof terms are at the bottom, this is an application, this is an abstraction, and this is a variable. So which rule applies is based on the structure of the proof term in the conclusion, if you're working backwards. If you're starting at a conclusion, you're saying, well, if I concluded this, what rule was the last rule to be applied? Then the structure of the proof term tells you what rule was the last rule to be applied. Because the three variants of the language of lambda calculus are mutually exclusive. Any questions about that?
Question on rule 2, why are we calling it an abstraction? Why? I mean, I can see for 3 application, I see, function.
Hey, sure. What is 2 times 2?
4.
How do you know? Oh, no, sorry. What is the square of 2? I should have asked you the question. What is 2 squared?
4.
Okay, why do you know that?
Because I know that 2 times 2 is 4, which is the same as the square of 2.
Right. Okay. So then I ask you, what is the square of 3? And then you do the same process. You take 3 and you multiply it with 3, right?
Yes.
And so if I ask you to compute the square of any number, you'll take that number and you'll multiply it with itself, right?
Right.
So the question of what is the square of 2 the answer to that is a number. Whereas the question of how do I square a number is an abstract process. It's the idea that the answer to the question of how do you square a number is that you should take that number and multiply it with itself. So being a function definition, it's an abstraction of the process used to compute it when evaluated at any of its inputs, right?
Okay. So then rule 2 is more about how, like if you have a how-to, versus 3 is you just apply it.
So what
like-
you should think of them is as an introduction rule and as an elimination rule. So proof terms should represent proofs of the things that we have in our language right now. So when you think of what our language is, you shouldn't think of what the proof terms are. You should think of what the logical connectives are. So right now, we are working in a universe in which the logical statements that we can make are statements formed by implication. And then you have these logical atoms of the propositional variables, right?
Yes.
So the expressivity of our logic is just the fact that you can state statements like that. Then the introduction rule is something that lets you form from the premises an implication. So if you have a proof of W in a context where you have a proof of T, then you can form a proof of T implies W, and the proof term tells you, this rule tells you how to form the proof term. Whereas the implication elimination rule is if you have a proof of an implication and you have a proof of something that you can feed into that implication, then it tells you how to use an implication. So this lets you construct implications, this lets you use implications. Hence introduction and elimination. Does that make sense?
Yes.
Okay, and now the motivating goal is that we want to take these rules and we want to write a program that when given some conclusion, when it's supposed to check proofs. So we give it a proof term, we give it a proposition, in other words, a logical formula, and I'm going to make the claim that my proof term proves the logical formula. Okay, what would it mean for that to be true? Anyone?
Could you repeat the question?
So let's suppose that I have a proof term,
Yeah.
in other words, some lambda calculus term, and I have some logical formula.
Okay.
And I claim that in, let's say, the empty context, if the context is empty, then I write nothing here, that in the empty context, my proof term, which I'll say is T, is a proof of T. What would it mean for that to be true?
I should be able to reconstruct the type from the proof.
And what? Well, the reconstruction uses information about the type, but this algorithm will do something, which, okay, what is the standard before we don't have the algorithm yet. We haven't discussed the algorithm, right? But there is a standard of correctness for what a valid sequent is. So for example, in the empty context, lambda x dot x is a proof of A implies A. And the idea is that, well, what is a proof of A implies A? It is a function that takes a proof of A and returns a proof of A, right? What is that function? It's a function that takes something and returns what you just gave it, right? So the assertion that this is a proof of A implies A is true. But you can also write false assertions. For example, you can write that in the empty context, Z is a proof of A, which is false. Z is meaningless. What does it mean that Z is a proof of A? So this statement is true, while this statement is false. How do I tell the difference? Or rather, not how do I tell the difference, but what does it mean for a sequence to be valid?
Well, are we still coupling the X term to A in the second example, which would be why it's false? Or is it like a wholly new thing where we didn't?
Oh, okay. Well, that's one reason to see why it's false. How would you see that something is true? What would it mean for something to be true?
If like for example, if something implies A, that probably means that lambda that's something dot something implies A to A, right?
What I'm looking for is what's a purely mathematical definition of all valid sequence?
Well, you have a grammar, so it has to fit one of the syntaxes, valid syntax.
Of which grammar do you mean? The proof rules or the terms? Do you mean this grammar or do you mean the rules?
Depends which way you're going.
Well, the question was, what is the standard of correctness of, no, what is a purely mathematical definition of all valid sequence? And you said it comes from the grammar.
Yes.
Which grammar does it come from?
The types.
For the types, right? You said
Yes.
this grammar.
Type.
Okay, how does that grammar tell you what the standard of correctness is for sequence? This grammar doesn't even talk about sequence, right?
But it tells you how to form them.
It tells you how to form types.
Yeah.
And the grammar for terms tells you how to form terms. Now, what is the grammar that lets you, well, it's not a grammar, but what lets you form sequence?
Is it the three rules above? The
Yes.
yeah.
So those rules, they're not a grammar, they're inference rules, right? So they tell you how, they are the rules of thoughts. These are rules which encode all valid logical deductions that you can make about implications. And then all possible valid sequence are constructed inductively by the inference rules. The inference rules inductively construct proof trees, and a sequence is valid if it's the conclusion of a proof tree that you can construct using those rules, right?
Yeah, for example, for the first one, I can use implication, the second rule, essentially. The first thing that you said is correct. I can
Right.
apply that rule, then do something else, which will be true, I think. So that it arrives at the var rule eventually, right? So I can derive it out of nothing.
I mean, so let's do an example. So I'm going to scroll down and now the rules aren't visible, which is unfortunate. But so here's the simplest example then. In the empty context, I claim that lambda xx is a proof of A implies A. Okay, how do I construct a proof tree for this? What rule do I use here?
Implication introduction.
Yep. Then what's do I get here?
Then you get that x of A yields, turnstile x of A.
And what's the justification for that?
Variable with an
Yes.
empty context.
There are no assumptions, and so this is a proof tree. This is a proof tree.
A question?
Yes.
I'm still having trouble like going, you know, building the tree from bottom up. I can
Well,
see.
we're about to
So-
discuss how computers do that.
Okay, so for instance here, we are talking about implication introduction for the bottom.
Okay,
Because
so
we-
I ask you the question, why did we use implication introduction?
Because when we look at the inference rule, that's the construction that it has.
What does that mean?
I mean, it looks like it. So
How do
when
you
I'm
tell
looking,
that you should use this rule as opposed to the other rules?
because I have a lambda, I have an xf
Yes,
dot,
exactly.
t.
So if you look at what the proof rules have, is that if you look at their conclusions are sequence. Every single sequence is a context, maybe the empty context, turnstile, proof term, colon, type, right? And proof terms are defined by the grammar of lambda calculus. And the grammar has 3 mutually distinct variants. So the proof term in the sequence is going to be one of 3 variants, and it's always possible to tell which one. Well, each of the variants appears in one and exactly one proof rule, which means that if you did some deduction that eventually let you conclude that that proof term was a proof of something, then you know which rule you had to apply.
Okay, so it's just a little bit rule. Okay, so I'm looking at a rule. I know you explained this before, but so that rule says in the context of gamma, X has type T. I'm not sure exactly
proof
what
rule?
that means. For implication introduction, just the rule that we're looking.
Okay,
We're built,
X
yeah,
is a variable, right?
yes.
We are going to assume a variable is just a name, right?
Mhm.
Our assumption is that that name refers to a proof of T.
Okay. So it's the same thing as saying X is a proof for T? When you say X
Yes,
has
X is a
type
proof
T,
of T.
it's the same as saying X has type T.
Yes, exactly. X has type T is the same as saying X is a proof of T.
Okay, thank you.
Any more questions? Right, so here in the proof tree, what we had is we were trying to construct this tree from the bottom. So we were just given a sequence and we tried to verify whether it's a valid sequence. So the question is, our question, this is the motivating question. Given a sequence, gamma, T, T. How do we determine whether it is valid? And the standard of validity is that i.e., is it the conclusion of some proof tree? Is it the conclusion of a validly constructed proof tree? right?
Yeah. Yeah.
And one of the things that we saw is, well, we can try and construct the tree. We can assume that the tree exists, give the sequent the benefit of the doubt, but then we know some things about the tree. If there's a valid proof tree, we know what rule had to be applied at each step, just because of the nature of what the rules look like. So to answer this question, observation 1, is basically that the structure of the term in the conclusion of a rule determines the rule used. And this is in a valid tree, in any valid tree. And so that's one of the biggest things that we have going for us in answering the question of how do I algorithmically verify a sequence, right? And then let's say we consider another sequence. Which one am I going to do? So I'm repeating the example from last class, and I'm doing this because I think it would be better to repeat it. Right, so suppose we're working in the empty context, and we claim that lambda x, lambda f, and then we take f and we apply to x, that this is a proof of, let's say, A implies B, implies B. And by the way, when I write it like this, parentheses are, arrows are implicitly right associative. So what's currently written on the screen really means this. So let's say my claim is that that is a valid sequence. How do we check whether it's a valid sequence? What do we do? So we try and construct the proof tree, because the standard of what it means to be a valid sequence is that it's the conclusion of a valid proof tree. Okay, if we try and construct the tree, what's the last rule that we had to have used?
Introduction
Yes. Why?
is the conclusion is the proof we got is an implication.
Is
So-
a no, not
No, the
the proof is a
wait.
The
I
logical
mean, the
formula.
type is
the formula is an implication, but that's not what it tells us. It's the fact that the proof term is the word that you're searching for is abstraction, right?
yes.
You could have also said a lambda, and I would have said, and then I would have said, yeah, correct, and that, but it's called abstraction. But yeah. So the structure of the proof term is a lambda. Yes, it's true that the logical formula or the type is an arrow, but that's not what's important. What determines the rule is the proof term. And so, okay, then what would the premises of the rule have to be?
It would be x:(a) yields
Right.
the lambda f dot fx expression colon a to b implies b.
Yeah. So we assume A in some sense. We strip the lambda and move X into our context with type annotation A. And then we're looking at the body of the lambda. And that's just lambda f is lambda f of X. Notice that X is meaningful only because it's being given meaning in the context. And so we'd like to say we are claiming that this is a proof of A implies B implies B. Okay, well, this isn't a valid proof tree yet. We need to continue. So what's the next level?
Another introduction because of lambda.
Mm-hmm. And so what's the proof term? Sorry, not the proof term. What's the premises? What's the sequent that's the premises?
Will be X is a proof of A, and F is a proof of A implies B.
Mm-hmm. So that's the context. We've, in some sense, assumed A implies B and let F denote a proof of it in logic speak. And so in that context, what are we claiming?
F of X is a proof of B.
Now what rules do we have to apply?
Implication elimination.
Right. Now, what's the context?
The context is X colon A comma F colon A to B. Just the left-hand side, that turnstile.
Yes. So the context doesn't change. And there are two things that we have to show. We have to show that F has type something, and then we also have to show that in the same context, that X has type something. Now, if we look at what the rule is, we have this occurrence of T in the rule at the top and twice in the top, but it doesn't occur in the bottom. And so that's a bit of an issue because we don't know what to fill it in with what to fill it in. And so there we get for the moment question mark and question mark. I guess we do know, though, that the proof has to look like something implies B. But at the moment we have question marks, right?
Yeah.
Now, if you actually look at it, F was assumed to have type A to B, right? Or A implies B.
Yeah.
And so that suggests that there's a definite way to fill that in. What should the question mark be filled in with?
A.
But that thing that we just did right there, that's a different process than the process that we were working with before. We actually had to look up F in the context, right? And that's a completely different process. In each of the previous steps, we didn't care what was in the context. We just added things to the context. But now we actually did something. So that's a different type of thing. But suppose that we do that type of thing and we determine that there should be an A here. Then how do I continue justifying this tree?
Then it will just be the variable rule.
Yes. So
Because-
there are two premises, right? This premises and this premises. And each of these premises are justified by var. And so that's a complete proof tree. So for example, if our algorithm was able to do this and it was able to fill in the question marks, then it would be able to verify the sequence. Does anyone have any questions about that?
So when we say a question mark is A, are we absolutely sure that there couldn't be like other big letters, what they called, terms or something that could also satisfy that with F?
So
yeah, it's only given the context though. So
yes,
yeah,
we're going to define rules, and we're going to show that, for example, well, we can show things. You can prove things about the rules as well.
Yeah.
However, the only thing that you know about X is that it has type A, right? You really can't show that X has type anything else. The only meaning that X has is from the assumption.
Yeah. So that's probably why we always start from empty context. That way we always know what our context is going to be.
Also, typically we say that something proves something. Well, you can also talk about, does something prove something in a context in which you have assumptions?
Yeah.
So you don't have to start at an empty context. You could have started, for example, at the second line. That would have been legal as well, right? If we remove the bottom thing, we still get a valid proof tree.
Yeah. Yeah.
But the fact that you have context is something that happens when you start making assumptions. So in general, the question should be checking a sequent where the context might not be empty. Because even if you start with an empty context, the question eventually becomes the other one, right?
Yeah.
Okay, and so really then we say, okay, this motivates two computational problems. The first is type checking. And this is given gamma, t, and t, determine well, rather, we are going to write a type checking function. Given gamma, t, t, and t, what our function is going to do is it will return true. Type checking given t return. Well, if our type checking function returns true, by the way, in full brackets, the value for truth isn't hash true, it's just hash t. So our type checking function will return true if it succeeds in constructing a proof tree. Else fail. Else it'll throw an error. In the same way that, for example, multiplying Booleans through an error, you'll get red output. But type checking isn't enough. Sometimes we're actually going to have to find what the type is, and that's called type synthesis. Given gamma and t, if our function can show that there is a unique unique conclusion. Gamma TT. So we're trying to, we're still trying to, we're basically given a proof and we're saying this is a valid proof. And also you can just by looking at the proof determine what theorem it's proving. So when type synthesis returns a type, it will have only do so when it's able to determine that there is a unique sequence, unique valid sequence of this form. There is a unique conclusion. If our function can show that there is a unique conclusion, then it will return true. No, then it will return the type. Else fail. Else it will throw an error. Any questions about this?
I have still a question about the proof that we're looking at, the proof tree. So at the
What
top
about?
level,
Sure.
So we arrived at 2 rules of bar. How did we do that? Like, how do we see that
Well,
from the level below?
look at F. Look at F. What type of lambda calculus term is F?
What type?
Not what type, what kind of, which variant of lambda calculus term is it?
That's a function, right? Or I'm not sure.
It's a what?
Can you repeat the question, please?
You asked why did I use the variable rule in this case? How do I know and why is the rule justified, right? My question is, look at that sequence. Its conclusion, well, the conclusion of the rule is a sequence. The sequence has a proof term. What kind of proof term is it?
It is a introduction elimination.
That's not a kind of proof term.
Proof term.
A proof term is a lambda calculus term. There are 3 variants in the grammar of lambda calculus, right?
Mm-hmm.
I'm asking about this proof term right here. Which kind of proof term is it?
Just looking at F, it would be a variable.
Yes, correct. So which proof rule is the only proof rule that will allow us to type a variable?
The first one.
The variable rule.
Variable. Mm-hmm.
And how do we type a variable? The only way that we know the type of a variable is if we have it in our context.
Okay.
By the way, contexts are considered unordered, except for the fact if there are conflicting names, but we'll ignore that for the moment. So here, really, this rule also A is in the context, so we can type A as A. Here, F is in the context, and we already have a type for it, right?
But in the line below, the level below F is to the left.
You're asking about this?
Right. Okay. So, but we have F in the context and behind the turnstile.
Yes.
Are those different Fs? Right.
I don't say your question. I didn't hear you.
Oh, yeah. So we see F is in the context, so to the left of the turnstile, but we also see it to the right of the turnstile.
Yes, correct.
So it's already in the context. So what does the the next level up give me that's different?
Well, look at the proof term. The proof term changes. Okay, so the question is, I'm assuming that F is a proof of A implies B. I'm assuming that F is a proof that if I'm a millionaire, I should get a yacht. And then I'm also assuming that I'm a millionaire. And then the claim is that applying one fact to the other will allow me to conclude that I should get a yacht. Well, how do I check the claim? I have to check both assumptions. I have to check that indeed it's true that if I'm a millionaire, I should get a yacht. And I should check that it's true indeed that I'm a millionaire. Like if I say the statement f of x, f applied to x has type B is equivalent to saying that I have some proof that I should get a yacht. Just colloquially, how do I know that I should get a yacht? That's a very bold proposition, right?
Mhm.
How do I check that I should get a yacht? But I'm not just saying that I should get a yacht. I'm saying that applying f to x is a proof that I should get a yacht.
There has to be an implication. If you're a millionaire, you should get a yacht. So that the implication should exist, that connection. And then the second question is, are you a millionaire?
Right, and the reason that I'm checking those two questions is because that I said that the proof of it is a proof which is an application, right? For example, if I already knew that I should get a yacht, then that would also be a proof of the fact that I should get a yacht, right? Let's suppose in my context I had a proof of B. Well, I'm not just saying that B is provable. I'm saying specifically that f of x is a proof of B. So I'm not checking the statement that B is provable. I'm checking the statement that f of x is a proof of B. And there's only one way to do that.
Okay, so that's what that top level says, that there's two separate things to look for.
So once again, look at the rules. That's all there is to it.
Mhm.
It's just applications of these rules. So I've justified the rules to a reasonable extent, and I've also justified how to think about them. But you're not going to get to, I'm not going to just intuitively tell you high-level things, and then suddenly you're going to know the proof rules. You need to look at the proof rules. You need to convince yourself why the proof rules are valid, and then you need to justify things by proof rules. This is about rule following. So if you have a question, then the question is that you don't understand how the rules were applied in this case, which isn't the case. You do understand how the rules were applied, right?
It's a lot of symbols, but
well,
yes,
sorry, with this we're going.
In general, yes. In general, yes. But I still have questions about it. How to go from one level to the next.
We're in the middle of class, so this is bits too off topic. If you have a concrete question about something that I just said, then that's one thing. Do you have a concrete question about something that I just said?
I'm good for now. Thank you.
Okay. Anyone else? Right. Okay. So the idea is that we are going to write two functions. One is a type checking function and one is a type synthesis function. Now, how I'm going to write what these functions are is that I'm going to write what essentially look like inference rules, but that I would recommend not thinking about inference rules, although logically they may be. So here are the rules that tell us how to write these functions. So first off, let's suppose that in some context in which I have that x is a proof of t, I try and verify that x, you can synthesize type t from x. So this is synthesis mode. I should write that. So type checking will be denoted as gamma t type checks to t. So here you were given t and you're trying to see whether t will accept the type. Whereas in type synthesis, you're not given what capital T is, and you're trying to squeeze the type out of t. So then if I'm trying to type check, sorry, if I'm trying to synthesize the type of t, I look it up in the context, right? So this seems to be a rule that's valid. However, that rule is a bit misleading. I can write the rule in a different way. Let's suppose that I just have context gamma. I don't know anything about it, and I'm trying to type check x as a proof of t. Then what do I do in order to determine whether, what do I do to synthesize, I'm trying to synthesize the type x of type of x in some context. What do I do in order to synthesize the type of x?
By checking whether x is within the context.
Right, so you look up x in the context. So the way that you do this is that you check that x is in the context, but we can write this as saying, for example, this is in the context. So this says do a lookup. So in this way, the rule doesn't just look like an axiom, it looks more like a command. If you're trying to synthesize the type of x, look it up in the context. And then if it has a result, then that's what you return. So this rule looks more algorithmic, a more algorithmic way to write it. Okay. Now let's say that in some context gamma, we are trying to check whether a certain lambda term has a type T implies W. Then what do I do in order to check this? What do I need to do?
So we check that given the context gamma and the context that x is a proof of t, we can check whether W has a type T.
Whether what has type T, whether what has type what?
Well, it's the other way, I think. Is whether T has the type W.
Yes. So, and then the computational interpretation of this rule is if we are trying to type check a lambda against some type, the first thing that we do is we have to verify whether that type is an arrow. If that type is not an arrow type, for example, if we try and type check whether lambda has type A, whether it'll accept type A, then that's an issue because lambdas always type as arrows. So we have to check whether what we're trying to check is indeed an arrow type. And then after we do that check, we throw in x into our context with a type annotation t, and then we try to check the body of the lambda against W. Then our third rule, so by the way, the two rules on the left are the same. these are the same. So this rule was the rule where we really encountered a problem. Let's suppose that we're trying to, in some context gamma, we have an application, f of a. And we have type W. And it's not clear whether we're doing checking or synthesis mode yet, right? Well, I mean, are we going to be able to type check f of a to W? Well, okay, we might be. But what we saw before is that what we'd have to do in order to do this is that the type of f, we don't know what to put for t. So we should enter synthesis mode, and we should synthesize its type. And this output of synthesis should be an arrow, otherwise it fails. And then we look at the first thing in the arrow, and then in the same context, what do we do with A?
See whether that has type T.
So synthesis or checking mode?
Checking.
Yes. So we synthesize the type of F, and we check whether A has type T. Now, does that let us? So remember, F synthesizes the type T arrow W means that there is a unique type with such that F has type, that type is a conclusion of a proof tree. So no matter what, the only valid thing to write here is T implies W. Then what is the only valid thing to write for the application f of A, provided that A type checks to T?
I think synthesis.
Yes.
Yeah.
So if F has a unique type, T implies W, and if A type checks to T, then we can conclude that the application has a unique type W. So algorithmically, what this rule means is that if we're trying to do this synthesis problem, the first thing that we do is that we do this synthesis problem. Then if that synthesis problem fails, it fails and throws an error. If it doesn't fail, then it returns some type. Then we have to check that that type is an arrow type. So one, in order to do the synthesis problem, one, you do this synthesis problem. Two, you match the type that's returned against an arrow type. And then three, you do this type checking problem. And then each one of those three steps is a place where the computation could fail. It could happen that the type synthesis fails on F. It could happen that the type returned isn't an arrow type. And then even if both of those succeed, it could be that A doesn't type check to T. But if all of those happen, then you're finally able to solve the original problem, which is the synthesis problem. And you can synthesize type W. Then, well, what happens if, for example, we want to check whether an application has type W? Well, in general, if we're able to do, so let's suppose that in context gamma, we're able to synthesize the type of, sorry, what is one way to type check the type of T? Or okay, that's a vague question. So suppose that we're able to synthesize the type of T. Then we should be allowed to type check T, right? This conclusion says that there's a unique proof tree with the conclusion gamma T colon T. And this says that there is a proof tree with gamma t colon t as its conclusion, right? So our algorithm should be allowed to make this deduction. And this new rule is called the turn rule. These rules are still called what they're used to be called. So this is var. This is implication introduction. And this is implication elimination, but in bidirectional form. And that's the turn rule. But at the same time, that's not a computational way to write it. The computational way to write it would be, let's suppose that you're trying to run the type checking problem, right? So what do? You run the type synthesis problem. What's the inputs to type synthesis? What is the input to type checking?
We are sort of trying to synthesize a type and see whether that is equal to the type T.
Well, my question is, in general, when you do any type synthesis, right? What is the inputs to this type synthesis problem? So here, for example,
The proof term
not only that.
and the context.
So if you're given only the proof term in the context, then what type of problem are you doing?
I thought it was type synthesis.
Yes. And what about type checking? What are you given in type checking?
Okay, the other way around. You're giving a type and you need to get the proof term and this
Nope.
context.
You're given the proof term. You're checking whether the proof term has that type. You're not
Okay.
trying to construct a proof term.
Okay, checking. Okay, thank you.
So in other words, what is the input to type checking?
Is the context and the proof. I mean, T.
No,
Little
for type checking.
for a checking, then that will be lambda small t and big T, capital T. So is the proof term the context and the type that we are trying to check?
Yes, good. So the input to type checking is three things: a context, a term, and a type. The input to type synthesis is two things: a context and a term. So here, if we're going to apply the turn rule, then the original problem that we're solving is type checking, right? So that has three things, right? So let's say we do synthesis. What's the inputs to synthesis?
The context and the proof.
Yes. And then suppose that synthesis outputs something. Let's call it W. Then what's the next thing that we do? So type synthesis gave me something. W is the output to type synthesis. Then what do? I'm trying to check T against type T.
Yeah. We see if the W and T are equal.
Yes.
Not, yep.
So let's write this triple arrow for the moment. This means that whatever the output is, we check that the output is equivalent to, or in this case, literally the same as, equal to the input. So this means check, let's say equal TW in racket. That's what the code is going to be. Now the turn rule will apply when no other rule applies. So for example, if you're trying to type check a lambda, you would not go into type synthesis mode if you could help it. And then finally, well, when, so then we introduce another thing, And this is just going to be a convenience for Proust. So when can we go from synthesis mode to checking mode? So suppose that we know that T can type check to T. When would we be allowed to conclude from that some term synthesizes type T? Does that look like something that should be generally reasonable? If I put T there, is that true? Should this rule be allowed?
No.
Why not?
Um, because we had it the other way around, just right above that, and reversing that doesn't seem correct for me.
So what does it mean that T type checks to T in context gamma? Well, when is a sequent valid, right? This means this will return true if the sequent is valid. When is a sequent valid? What is the criterion for a sequent being valid? Anyone?
I think previously we said that the inference rules tell you which ones are valid.
How do they tell us which things are valid?
You should be able to apply only one at any given time.
No,
So
that's
should-
just an observation that we made that'll help us algorithmically verify it.
Okay.
Stating that observation isn't necessary for stating what's the criterion for validity is.
Okay.
The question is, you have a set of inference rules. How do inference rules determine valid sequence?
We check whether we can form a proof tree.
Yes, a sequent is valid exactly when there is a proof tree with that sequent as its conclusion. That is how a system of inference rules determines all possible valid sequence, right?
Yeah.
Were you going to say something else?
So I think we are checking whether T has type T in the same context. Question that we are asking.
Going back to the bottom?
Yeah. I think we are trying to synthesize the type T is a proof of T, right? And we give the type T, the synthesized type T.
Well, if our program, for example, returns that T from T you can synthesize type T, what does that mean?
That means we can conclude that given context gamma, T has type T, right?
It means something stronger.
Stronger.
I guess, like, since we have it on the line before, if we evaluate the type check of little t with t, then if it's true, it could yield the next line, since that implies that through the process of type checking, little t would yield big T.
Well, so this says that the program succeeds in constructing a proof tree, right? So if it returns true, then there exists a proof tree with that as a valid sequent, right?
Oh yeah.
That's for type checking. Now, what about type synthesis? If our function returns t, then what is the function theoretically required to do ahead of that? It has to show that there is a unique conclusion. There is a unique tree with anything in this position, right?
Yeah.
So the type, it's not only that little t type checks to t, it's that there's nothing else to which it could type check, right?
Yeah, because of the next line with the synthesis.
So if the above statement returns as opposed to throwing an error, then what does that mean?
Then that means that is a valid proof tree.
There is a valid proof tree, right? And what does the bottom line, if it succeeds, mean?
That means that it can conclude a proof tree with that given.
No, the synthesis is stronger. What does synthesis tell us?
There's a unique conclusion.
Yes, that there is a unique conclusion. So this tells us there exists a conclusion, which is T is a conclusion, that T is a valid conclusion. This says that T is the only valid conclusion. And so this rule shouldn't be allowed. Which is why if we are going to switch modes, we need some big hints. And that's why we introduce a new piece of stuff into our grammar, and that's called a type annotation. So T will you'll only be able to synthesize its type if there's an annotation that says, for example, T has type T. And so this is called an annotation. And the only purpose of an annotation is to allow us to switch from synthesis mode to checking mode. And this rule is correspondingly called the annotation rule. So this rule exists for the sake of making it easier to write things in Proust. Exists as a convenient notation. Notice that none of the other rules introduce annotations in proof terms. It looks like contexts have annotations, but contexts, it's just a coincidence. The contexts, the proof terms are variables. They're not annotations, they're variables. So none of these rules introduce annotations, whereas this rule gets rid of an annotation. And so this collection of rules actually tells us what our proof checking algorithms are. This completely specifies what the algorithms are. So for example, if we were doing the thing that we did above, the way that we'd run the program is as follows. Oh, okay, it's going to make me do this. That's a bit annoying. No, I do want to erase all of the types, right? And I also want to erase the colons. So suppose that we start off this algorithm in type checking. Suppose that's our first goal is to type check this. So I'll now show you how the algorithm works. So how do we type check a lambda? What's the rule for type checking a lambda? Anyone?
Oh, that's just
I mean,
the
go ahead.
implication introduction again.
Yes. And what did the premises have? So we're going to do something with A implies B implies B. And what does it say that we should do? Checking or synthesis?
Checking.
Right. And here's why, one reason why it's checking. I wrote this, right? I wrote down the type. In synthesis, we don't even have the type. So the fact that I wrote down the type suggests that it would be checking. So we started with the problem of checking this term. Then we got to the problem of checking this term, right? Then what happens next? So what rule do we apply?
Elimination.
No, for this step.
Oh,
So we apply the rule again, right? And
Yeah.
now what are we doing? We're checking whether this has type what?
that's type B.
B.
Yeah.
Now, look at the proof term. What kind of lambda calculus term is that?
The application.
Yes. So what proof rule do we use?
Elimination.
Yes. But now here's the interesting thing. If we look at the proof rules, implication elimination operates in synthesis mode.
Yeah.
Not in checking mode. So now we actually have to change our proof tree. So implication elimination actually operates in synthesis mode, but we're in checking mode right now. So what do we do? None of the
Turn.
rules apply. Yes, only turn applies. If no other rule applies, you use turn. And so what does turn do?
It just changes the tab checking to synthesis
Yes.
with the same context.
So let's write it like this. So right now we're trying to synthesize the type of f of x. And we don't know what it'll synthesize to. And then later, whatever it is that we get, we should check whether that's equivalent to b, right? So right now, it's a very good point to pay attention because after I've written everything down, it'll make less sense than as I'm doing it. Because I'm showing you what the algorithm looks like. I'm filling in the blanks as we go along. So right now we're doing a synthesis problem, right? As we're doing the synthesis problem, we don't know what we're going to synthesize at the moment. But what rule are we going to apply?
Elimination.
Yes. So now that we're in synthesis mode, the implication elimination rule applies. And what does that tell us? How do we synthesize that type? What do we do?
We see if F synthesize, if F can be synthesized to of type
Some
T.
T.
Yeah, some T.
Right. And then later, after we synthesize that type, we're going to have to check something, right?
Yeah.
Let's say that X has type we don't know. We're going to check that X has some type. We don't know what that type is yet. Okay. Well, how do I synthesize the type of F? What rule do I apply?
Var.
Yes. And what does that require me to do? Well, what am I doing computationally when I invoke var?
Checking within the context.
Yes, I'm doing a looking up in the context. So I look up F in the context. And so let's say this is my context. I'm going to put squiggly brackets around my context. And so I look it up in the context, and what do I find?
F has type A implies B.
Yes, so our context tells us that F has type A implies B in context, which means that I'm able to synthesize the type of F2.
A implies B.
Yes. Now that I've synthesized the type of A implies B, I look at this type and I notice that it's an arrow type, right? So it's an arrow type. It's something implies something. And so what do I do with the left-hand side of the something?
We check whether X has type A.
Yes. So now I put the A here, and now I'm trying to do that checking, right?
Yeah.
Well, how do I check whether X has type A? What am I forced to do?
Turn.
Yes. In order for variables, my rules say that I can synthesize variables by context lookups. So I turn. Now turn mode puts me into synthesis, so I don't know what the thing here is yet. And then I'll eventually check whether whatever I get, I will check whether that's the same as A. But for now, let's do this. Okay, what do I do here? I'm trying to no, there's a typo. In that context, I'm trying to synthesize the type of what?
X.
Yep. And how do I do that?
Var.
Yes. And so I go to my context, I look at X. And I look at my context, it's what I wrote before. And what's the results of my context lookup?
It's access type A.
Yes. And so what's the result of the synthesis?
It's A.
Right. Now, I look at this A, and that's what I'm checking is equivalent to A. Is that true? Is A equivalent to A?
Yes.
So in other words, this checking now succeeds. X type checks to A. So what does that tell me now? Now that I've managed to do that type checking, what was I doing before? I was trying to synthesize the type of this application. What does implication elimination tell me that the type should be?
B.
Yes, because whatever I synthesized here was an arrow type, and the right-hand side of it was a B. I should perhaps put green here to indicate that this A went to here. And so I am able to synthesize B. Now I need to check whether B is equivalent to B. Is it? Well, yes, it is, right? And so, in other words, the premises of this turn rule were satisfied. So I get to conclude this, which is this checking. Then I get to conclude this because the premises were satisfied. And then I get to conclude this. So this is what the algorithm will look like. This is what the computation looks like. It's bigger. You have instances of turn, and I guess I didn't write the second explicit instance of turn. This is also turn. And it's a bigger proof tree. But if you look at the proof tree at the end, it isn't as informative as when you do it dynamically. Because when you're doing it computationally, in all of the syntheses, you leave the places blank until you can fill them in. And now you actually see the order in which this computation happens. And there, I didn't have to do any creativity. I just followed the rules. And that's what the computer will do. So the starting version of Proust implements exactly this algorithm that I just outlined. Does anyone have any questions about this algorithm? And this is in Proust. Okay, let's take a 5-minute break, and then we'll restart at 3:35. I'll leave the algorithm on the slide right now. Any questions, though? So yeah, now you see that algorithmically, we have a few more complications thrown in because we have to change between synthesis and checking mode. But at the same time, there were no question marks. We filled in things when it was their time to be filled in. And there was zero creativity involved in doing this process. We started the bottom sequence and we just followed the rules. And a computer is able to do this. And I'll show you right now the implementation of how this is done on a computer after the break. Okay, see you in 5 minutes. Anyone have any questions for me to answer after the break ends? Okay, let's restart. Any questions? So our first order of business is to discuss several racket constructions that are relevant in Proust code that are not available in the student languages, but that are available in full racket.
Oh, we're back online.
Sorry, is that a question or?
We haven't really seen that. You need to.
Right. If you want to ask a question, unmute yourself. And now, so the three constructions that we're going to need to discuss are first quoting and quasi-quoting. Then pattern matching. Actually, all of these were available in the student languages as well. If you wrote the right require statements are already available. And then the third one is structures, which were also in the student languages. But pattern matching, you would have to explicitly write something to bring it into the student languages. It's not available by default. Although rackets, it has structures in a slightly different way than I introduced them in the first racket tour. So I'm now going to switch to Dr. Racket. Right. Okay, so first off, here I am in Racket interaction. the language is set to determine language from source. And unlike the student languages, I need to put a line at the beginning that says which language I'm using. In this case, #lang racket. So quote, and this is available in the student languages as well, is a much quicker way to specify lists plus other things. So at first approximation, this lets us specify lists with brevity. So for example, in the interactions window, instead of writing list 1, 2, 3, in fact, in full racket, if I run this, the output that I'll get is quote 1, 2, 3. Quote is a quick notation for constructing lists. So quote 1, 2, 3 is equivalent to list 1, 2, 3. But it actually does several more things. Let's say I have the letter A. Right now, that's a variable name. What will happen if I press return? Oh, and you're going to have to unmute yourselves, by the way, if you want to talk.
That just returns A, right?
Well, what is A?
A is a letter.
But grammatically, in the racket grammar, is it just a letter? So it's a name, and it'll say that A is undefined, right? Because, for example, if I write something like multiplication, that's a defined name, right? Instead of writing multiplication, it'll write procedure. And then if I write maybe lambda x times xx, that's also a value. It's a procedure value. But A is undefined. Now I can take the name A and I can transform it just into a name that is meaningless. And that's called a symbol. So quote of quote in front of a name transforms it into a symbol. And if I take a list and I have some numbers and then some names, then not only will quote make a list, but it'll also take all of the names in the list and transform them into symbols. So for example, I can take this list, and functions that are available in Racket are things like second, the second element of this list. Well, that's a number. Now what about the third element of this list? What is that going to be?
A?
Symbol A.
Symbol.
And it gets better. I'm also able to define lists inside of lists. So something like this. And I don't have to write multiple quotes. It will recursively make lists from all of the lists inside it and turn all of the names into symbols. So it recursively forms lists from parens and quotes symbols and quotes names. Generally, parens would denote function evaluation, and symbols would denote names. But under quote notation, names become symbols. Sorry, names would be names. But under quote notation, names become symbols, and parentheses, which would indicate function evaluation, instead become lists. And it goes down at all levels. So for example, if I took the third element of this list, what would it be?
It's gonna be symbol 1A, then 2, 3. I mean, it keeps the parentheses.
Well,
right?
quote, it's going to be a list, right?
Yeah.
And for example, that thing, that is the same as if I had list 1 quote A and then list 2, 3, right? So instead of writing this entire notation, I get to basically delete every single occurrence of list and every single quote and just put a single quote in the front. So that's quote notation is quick. It's nice. Now, the problem is, let's say I have something like define x3. And let's say I want to make a list in which I have the symbol A and plus x to adding 2 to x. So what would that give me when I run this?
It gives 1A, then x plus 2.
Yes, where x is now the symbol, and plus is a symbol and x is a symbol, right? So plus is just a meaningless symbol. But let's say I actually want to do this computation. Quasi-quote is like quote, but it lets you stop the recursive quoting. Via unquoting. And that's denoted by a comma. And the way the quasi-quote works is that we do a backslash instead of, sorry, a backtick. This is called a backtick. And then we take the expression that we had before. And right now, it's just going to do the same thing. But the key thing that it allows is that it allows us to escape this by putting a comma. And then the comma unquotes this. And now if I run it, it'll actually evaluate x plus 2. So quasi-quoting lets me prevent things from being symbols. And here's another use of quasi-quoting. I can also unquote, let's just say I have 1A and x, right? How do I get x is 3? How do I get 3 in this list?
Put a comma before x.
Yes. So that lets me unquote the name x, and then the name is not quoted and treated as a symbol, rather it's treated as a name and subject to evaluation. So unquoting does not work if you're working under a quote. You need to be working under a quasi-quote. Quasi-quotes are escapable quotes. So that's quoting and quasi-quoting. That was topic 1. That's just a quick piece of notation. Now, topic 2 is match. And this is a very overpowered feature. So for example, let's say that we have a structurally recursive sum list function. By the way, for the midterm, you're going to have to know that this entire function can just be written as, how do I just write this function very quickly in one line?
Using fold R, then plus.
What do I do?
Then it will be 0 and LSD.
Yeah. So this is how I write sum list using fold R. Let's call this sum list 2. Okay, well, now here is how I write sum list using match. So instead of going through a condition, what I'm going to write is a match statement. I am going to match the form of list. Now, if it's an empty list, I'll return 0. On the other hand, it has to be a cons, right? So what I say is cons, and then I introduce some symbols. Let's say that the first element is called x, and the remainder is called L. So X and L are not names that exist right now, but I'm matching the form of list as a cons statement. So this match statement says that list, if it succeeds, is of the form cons XL. And then what is my results for if X and L now makes sense? If list is of the form cons XL, then what should I return?
Plus X sum list 3L.
Yeah. So this is called pattern matching. And this lets you detect, for example, if a list is of the form, this is one of the things that lets you do, is of the form cons XL. And if it is, it introduces the names X and L for those parts. And so here, instead of saying first list, rest list, I've found that my list is of the form cons XL. Now, X is going to be first list, L is going to be rest list, but I didn't have to write that. I could just pattern match. So before I continue discussing pattern matching, I'm very quickly going to discuss topic 3, which is structures. Now, in full rackets, structures are actually a bit easier to use than in the teaching languages, although we didn't get through a very long instance of them. So I can say, for example, define structs. And let's say I want to define, let's do nats. Whoops. Anyway, here we are. So here's a racket implementation of nats. So first we're going to define a struct Z, which is going to have no constituent structure. And then we're going to define structs S, and this is going to have something inside it. Then the way that I can actually construct these in brackets is to just say Z. Here, I'll run these two definitions. I can construct struct Z just by saying make Z. And then I can construct an S struct by saying, for example, S of Z. Now, it doesn't provide as helpful output as it does in the teaching languages. So for example, it'll just tell me that it's the struct of the form S, but it won't tell me what's inside it. Now I can define, for example, plus. That takes two NAT values. So let's say that a NAT is either Z or S of some NATs. Then plus should be a function that takes two NAT values and returns a NAT value. Now, how do I implement plus using match? Plus uses the structure of which argument?
M.
Yeah. So what do I match M against?
Open parenthesis, Z, close parenthesis,
Yes. And then what do I return?
N.
In the case that M has this form Z.
Just N.
And what about the other case?
S.
And then what do I write here? So what should I type? It's one character.
Lowercase b.
Let's say K. In the notes we use K, right?
Right.
So NAT is either Z or it's the successor of something, which is K. And then what did the rule say? Then what should I return?
S of plus NK, like literally what we have.
So in the teaching languages, you had to write make Z and make S. But in full racket, you can just construct structs by using these names. Now, of course, there's a bit of an issue because we have bad outputs. So for example, if I ask what plus S of Z is with S of Z, then all it'll tell me is that it's a successor when it prints it out. So that's a bit useless, but we can write, for example, to number, which takes a NATS and returns a number. How can I define this? So this is like, I guess, a bit of practice.
You could use match again.
Yep. If it's Z, what number do I get?
0.
And otherwise?
If it's S of K, then it's, I guess, add 1 to num K.
Yep. And by the way, let's just write a function going the other way. Let's say X. Okay, what do I do?
Match X.
Well, sure. So X is going to be a number. What's the first case?
0.
Then
Then it returns Z.
and otherwise, so in a match, you can put, for example, underscore as a catch-all. But you don't have to put underscore. You can actually put any variable name. We can like say y. Y as a variable will match anything, right? Because it'll just, can you match X to a variable? Yes. X is the, Y becomes the variable. So I can show you, for example, in the attractions window, if I type in match, and then I match the number 3, and let's say the first pattern is X, and then if it's of the form X, then I return X. So what's that going to output?
S of y minus 1.
No, sorry, just here,
Oh.
match 3XX.
Three?
Yes, because I've matched 3 against a variable, and then 3 gets bound to that variable, and then if I output that variable, I get this. Similarly, I can do match x3, and then I can do plus 3, 5, and then I'll get 8. So here, underscore is also another variable name. Underscore is a valid name in brackets. I could have typed else as well. Else is also, oh, interesting. Okay, wildcard is actually a special syntactic form for match. Okay, so underscores serve as special names. They don't get bound to. I did not know that. Okay, so if it's anything else, then what do I do?
It's going to be S of 2 nat of sub 1x.
Yep. Now, this is going to be very sad if you pass it not a natural number to start with, but if we pass it natural numbers to start with, it's going to be fine. So let's check our things. So we can, for example, say, how do I test this? Let me do 15 plus 12 in that language. How do I test that?
$15 to $12. And plus, you mean plus 15, 12?
Plus, but what?
Well, there's going to be a lot of S's, right?
But I have a function that lets me produce nuts,
Okay.
right?
Okay. So it's 2 nat 15 and 2 nat 12.
So if I run this, it's just going to tell me that I get an S back because full racket is bad at printing structs. But what if I want to get a number back from that?
2 num of it.
So here, Racket converted 15 and 12 to NAT language, and then it actually applied the match pattern all of the times. It moved it over. It finally got to a NAT value, and then it converted it back to a number using match statements. So, and then the final case of a match statement is that I can actually take the sum list, or I could do the following thing, for example. I could do sum list 4, But instead of doing cons XL, I will actually write, for example, list X, and then I'll put a colon after L. So the list consists of X, and then it consists of 0 or more L patterns. And that will also work.
Question. Can you explain how that first part works that has list?
Which one?
Before it had something. Yes, but before it had cons XL.
This one?
How does that, yeah, how does that work?
So a list is either empty or cons of something onto a list. Then Racket is able to take this description of its cons of something onto a list, and it's able to pattern match list as being a cons. And then when it pattern matches it, X. So notice, if I highlight X right now in full brackets, if I go to any variable, I think this might have been in teaching languages, it tells me where the binding occurrence of that variable is. So if I go and I hover over L, it tells me that this L is defined here. This X is defined here. This sum list 3 is defined there. So this literally, Racket, this is a completely overpowered and magical feature. Racket just magically determines whether whatever you have is of this form.
So question, so why would you match in a sum list? What
Well, before we wrote cond,
additional
right?
power, yeah,
And before we had to say first list and we had to say rest list, right?
Mhm.
But what is LST? If LST is not empty, then it's cons first list onto rest list, right?
yes.
So here I say, well, it's cons first list onto X list, and then I get X and L. This definition right here is shorter than this definition right here.
Okay, so it's like a shorthand.
Yes, but it also lets you do things like structures. And then it lets you do things like are even more complicated. Here is match 0 or more of.
Mhm.
You can basically write grammar rules in here. It's almost as though it detects which variant of a grammar you have and follows that variant. So these statements are really, really brief, and it would be much more painful to write them without match.
And then on structure,
Yes.
you are telling it, okay, so when you say define struct, Z, okay, Z is the empty list, is that what it?
No,
you have?
Z is a structure. This
Right.
isn't a list. This just says that Z has no parameters,
Oh, no parameters. Okay,
whereas
and
S
then-
takes one parameter to construct an S.
So what would be an example? What
Well,
would what would
S
it
of S of Z.
Mhm.
Here is the number 2 as a noun. So I now have knots to racket. I've just added knots to racket. I've added knots to racket with these 2 lines, which isn't something that I had before. And then I can add knots. I can say, for example, plus that with that. So what's that going to be? How many S's are there on this one and how many S's are on that one? There are 1, 2, 3, 4, and 1, 2. So this is 4 plus 2. So it's going to return 6 as a nats, but I can't see that. But I can also say 2 num of this, and then I can see that I get 6. So there, we have nats and racket. It took 2 lines to get nats and rackets. It took 4 lines to define plus. This feature is absolutely magical. Like, it is very surprising that Racket can do this, but it can. But you haven't seen like more powerful uses. Here is match 0 or more of. So Prabhakar has a section in the Proust notes. He links to a resource on a write-up of how to use pattern matching, which I'll send you by email. But just to check that SumList4 works, for example, with this match 0 or more pattern, let's say I ask it to SumList, and then instead of writing lists, I can now write the much quicker notation. 6. And it gets better. You can also do things like so let's consider the following statement. Let's say we're going to match the list consisting of list 1, 2, and list 2, 1. So maybe this is the list of permutations. Or no, let's just say A, it's symbol A means 12, symbol B means false. So if I look at this list, for example, this is going to be a list which has 2 items. The first item is a symbol paired to a value, and there's another symbol paired to a value. Symbols are values as well. So if I take, for example, the first of this, actually in full Racket, you can also define things in the interactions window. So I can, for example, define L S list to be this. And then I can, for example, ask it to print list, and then I can say first list. And it'll be this. So it'll be, and then if I say first to first, it'll give me the symbol A. And if I take the second element of that, then it'll give me the number 12. So that's an example of maybe a lookup table. It binds symbol names to values. But let's say I want to write a match statement. I'm matching that. And then in the first case, can it match it against a list in which the first thing is X and the second thing is Y? Oh, by the way, what happens if there's nothing that you can match? So let's match 1 against 2. Then Racket will throw an error if there's no matching clause. So let's look at the statement. What's going to happen?
Is it going to match A12 to XY?
Well, let's see.
And then
No, it won't,
B.
because there's no matching clause for this. Now, why does that happen? Because right now, what if I put list? Then it would work. So for example, I could say X then that would work. But the problem is that list, now that I've quoted it, that becomes quote X, right? Oh, by the way, quoting, you can double quote a symbol. Oh, interesting. Quote also disables quote. But if you can quasi-quote, comma, quote symbol, then you'll just get the symbol back. So quote quotes quote. And then it's not symbol A, it's quote quote A, but if you quasi-quote and then unquote, then you'll get quote A, and then you're trying to quote quote A. Right. You can also type in quote. That does that as well. So the problem is that right now those are symbols, but I can escape them into meaningless names by doing quasi-quote and escaping them. And then this will work as well. So if I want to match against a list and I want to have variables names in the list, then I can quasi-quote it and escape the names. And this is used in proofs. By the way, you don't have to memorize this. This is just some pointers about how to understand the Proust code, which are going to be relevant when you're writing the code. But when you're writing the code, you can look these up. You can rewatch the lecture. You can read Prabhakar's document on pattern matching. Any questions? Is anyone impressed, particularly impressed with match?
Yeah, that's so cool.
The racket implementation of natural numbers and addition, that. Okay, let me open Proust code. So here is the code for Proust. So it starts with a bunch of comments and then it tells you what the grammar for Proust is. Because racket has a special meaning for dots, we replace dots with this arrow. And then we have annotations, and then later we have this thing called holes, which are unfinished promises for proof terms. They're promises. Then Proust, also in full rackets, in order to access things inside of structure, you just write hashtag transparent. Sorry, hash transparent. That's something that you're going to have to write for the structs that you defined. So for example, here, if I look at struct S of Z, that's a struct. Now, how do I access what's inside of it? I'd like to say S val. Oh, whoops. That's fine. Anyway, so all of the structs that are written here have transparent written after them. You should write this if you write any new structs. You're going to put them adjacent to here. So don't worry about what transparent does. The point is that there is going to be a struct for lambdas, a struct for applications, a struct for annotations, a struct for holes, and a struct for arrows. These are the structs corresponding to proof terms. These are the structs corresponding to types. Variables are going to be represented by symbols. So then parsing takes a quoted expression, a list, and it transforms it into a expression, which is built out of these structs. So for example, I can consider the expression, let's say, quoted lambda x goes to x. This is the identity term. Now that's just a quoted expression at the moment. Now, if I actually want to make a Proust expression with these structs, I need to parse that expression. And there are separate functions for parsing expressions and types. And then it'll be a structure. It'll be a lambda struct xx. And right now, they've decided to be generous and print what it is. So actually, let's see what happens if I put transparent here on these structs. And now if I consider s of z, what do I get? So now it'll actually print it. Okay, so that's one thing that transparent does. Now, before it just printed it, but now we can actually, for example, say plus 2 num 2 not 17, and then 2 not, let's say 23. And then I'll get this very big expression with a bunch of s's in it, which is chosen to print like this. Notice the large amount of closing parens. Let's be more 3 and like 2. So that's cool. And now if I see, it'll be a struct where the lambda struct has two things. It has a variable and it has a body. The variable is just going to be the symbol x, and that's the body as well. Then I can parse expressions like lambda x, lambda y, x. And then it'll just give me structure. So that's what parse does. Then there's also parsing for types. So let's say A to B to A. And these rules implement right associativity here. So if I, for example, parse this type, it'll give me arrow A to B to A. And then I can give the problem, for example, on the first homework. I believe that that was A implies C. What was it? What does anyone remember the problem of the first homework? I believe it was something like this. I'm not sure what the order was of the A implies B and the A implies C, but I think that's what it was. No, it was like this. No. It was A implies B implies C. Implies A implies B implies A implies C. And then if you look at what the structure of that is, well, what is that type struct? It's an arrow type. What's the first factor? It's A to B to C. What's the right-hand side? It's an arrow in which the left-hand side is A to B, and the right-hand side is A to C. Any questions about that? Okay, and then I have the opposite operation. If I have some type as an expression, so that those are called EXPRs and types, then I have printing functions. They're called pretty print type and pretty print expression. So let's say I want to pretty print this type, and it's the result of this. Well, so that returns a string. But if I also, let's say, for example, print that string, so that returns a string. If I print that string, it'll color it in purple. And then if there's a context, which is going to be an association list of names with types, sorry, of symbols with types, then I can print that context to a string. So an example of a context would be list, or let's do it like this. List X, and then let's make that quasi-quote, and let's unquote that, and let's put a type, like A implies B implies A. So that would be an example of a context. Just lists of pairs of symbols and types. And then I could say, for example, pretty print context. Now that's a new line. So right now, you wouldn't be calling these functions, they'd be called elsewhere. So right now you're seeing strings, but they will be in purple and they will not have these outer quotes. Okay, now here's the only thing that matters in this demonstration. Here are the type checking and the type synthesis functions. The entirety of Proust right now is contained really in these two functions. So what does this say? Let's say we're type checking in a context an expression of a given type against a given type. So does this expression type check to this type in this context? Well, okay, if it's a lambda, then I look at the type and I see if it's an arrow. And if it's an arrow type, then I take X, I put it into the context along with the type, and I type check the body of the lambda against the right-hand side of the arrow. And if anything else, it fails. Now, holes, let's not worry about this for the moment. And otherwise, the only other type checking rule that we have is the turn rule. And so you type synthesize context and expression, and then you check for equality. And if that succeeds, then you return true, otherwise you throw an error. So this is the implication introduction rule implemented here. This line is implication introduction, and this line is turn. Any questions? Okay, and then for type synthesis, there are no rules for synthesizing the type of a lambda, so you throw an error. Holes, let's not worry about it yet, but you can't synthesize holes. Annotations, how do you type check an annotation? Well, annotations are the only ones that let you turn type synthesis into type checking. Sorry, how do you synthesize? you can synthesize the type of an annotation by type checking it against what it's being annotated with. And if type checking succeeds, then you return the type on the right-hand side of the annotation. Now, here's the application rule. This is implication elimination. You synthesize the type of an application. Well, the first thing is that you synthesize the type of the function. And then we're defining that to be TF. Then you're matching TF. If it's an arrow type, we can do something. If it's not, we throw an error. So that's the second point of failure. It can fail here, it can fail here. But if the type synthesis succeeds and it is a type of an arrow, then we need to type check A against type TT. Now, that's what this when clause is in this match. If it succeeds, in other words, type checking succeeds, then we just return TW, the right-hand side. Then type synthesis succeeds. Otherwise, this fails, and we go to the else clause, and we can't synthesize. And then if you have a symbol, then you look it up in your context. And you use for this built-in function called association, for association list. And then in the Prabhakar's notes, he explains exactly how this works. Otherwise, you fail. So this right now, these lines are an implementation of the entire bidirectional type checking algorithm that we discussed before. This is how many lines it takes to teach a computer how to do what we were drawing on the page. In fact, this is more lines than it takes to do that, because what we're looking at right now but I actually want to open a different file. Here we are. That's the old version. This is the current version. This version doesn't have holes. And in this version, the functions are even shorter. Okay, here's type checking without holes, and here's type synthesis without holes. So this is how many lines it takes to teach a computer to run that algorithm. Any questions? Okay, well, now I'll go on and answer questions about the midterm. So I can go over time and you can ask about the midterm. Okay, midterm questions. So feel free to ask anything related to the course, except unless it directly pertains to your homework. This is your last chance to ask.
Just a quick one first. How many questions exactly will be on the midterm?
Well, there are 5 categories of questions, and then each one has 2 or 3 parts. Sometimes 1. So there are 5 broad categories of questions. I guess I ask you to do 3 proofs, 3 written proofs, then 2 Proust proof terms, and write, let's see. Okay, so I need to determine whether I'm putting a problem on or not, but 4 functions. And then there are going to be bonus problems. Oh, sorry, you're going to have to implement 4 things in Racket. Several of them are going to be structurally recursive, and then the other ones are going to be in terms of higher order functions, which do the structural recursion for you. So, but there are going to be 3 written proofs.
Okay, that's like gnats and lists.
Yes.
Okay.
2 about gnats, and 1 on list. And then 3 structural recursive 3 lists recursive functions. And then 2 or 3 higher order functions. Two proof terms.
Oh wait, didn't you say that there would be 4 functions? So how is there 3?
Okay, so I'm still fixing this. Oh, okay. No. There are definitely, I can say 2. So there are still some things that I'm adjusting, placing on or off. I have a list of problems and I need to still put it up on Marmosets. Oh, okay. I guess the biggest FAQ is I reserve the right to slightly modify problems until noon tomorrow. It's to fix broken problems until noon tomorrow. Like make actual changes that change the problem statement. I'll fix typos after that as well. But there might be some changes which I'll attempt to do to fix problems until noon tomorrow. And I still need to do marmoset tests for some of these. So those will be up by today midnight. But remember, the exam ends on Wednesday at noon. Is the deadline. And this is a hard deadline. I am not going to accept exam problems after this. So this is this is a hard deadline. This isn't like homework problems where I've been super lenient about it. In fact, I haven't rejected any homework problems at any point. Okay, then 1 miscellaneous problem, 1 easy miscellaneous problem. And then 2 or 3 bonus questions. The reason that I say 2 or 3 is because I was not able to solve one of my bonus questions in 25 minutes, and I need to ensure that it's doable. But if it's doable, then I'll also put that on.
Professor, do we still have class on Wednesday?
We do. The exam is due before class, right?
Yeah, that's why I just wanted to double check.
Yeah. Yeah, we're on a schedule, so I can't. Class is happening on Wednesday. Okay, well, that's just the outline. You're going to see this there, but these topics basically correspond to the homework problems as well, but they're not going to be literal homework problems. Okay, go ahead.
So the easy quote unquote miscellaneous question, is it gonna be conceptual or something concrete?
It's going to be fairly concrete, and you're going to have to explain something, but you're going to explain it without proving it. So this is just about the behavior of Racket. Don't worry about it. It's doable. You can do an experiment for this. Okay, so what are you allowed to access for resources? You are allowed to access, well, I've written it in an email, but I guess I'm adding some things to that. You are allowed to read the Piazza, but not posts. And then also the notes, the lecture videos. Then Lackey. And then Prabhakar, actually anything on Prabhakar's website. So he has, for example, Racket guides there. But mainly, and then also emails. You're allowed to read emails that I've sent. And then things unrelated to the course. So it is not against the rules to discuss non-course related things again with people on Facebook. That's fine. But you're not allowed to discuss course related things with people on Facebook for obvious reasons. And I think you should be able to tell the difference between these on your own. And then if you really think that something's ambiguous, you can send me an email, although you probably don't have to. Okay, and then you are also allowed to email me during the exam, but I won't answer theoretical questions about the material. If you think that there's a mistake or that there's a mistake with Marmoset, then I very much ask you to email me because there might be mistakes. So this is like when I say please email me about any errors, it makes my life much, much, much easier if people tell me about any errors that you find very early on. And then don't access other, don't look at other things. And no looking up course-related content on Google. No searching for course-related content. And one of the ways in which this is going to be made very hard is that I should emphasize this. For all of these problems, they must be structurally recursive. And there will be a whitelist of allowed functions of allowed language constructs. So in other words, there are very big restrictions on how you can write this. So you have to solve the problems using a very small toolbox, and everything that you write for these problems has to be structurally recursive. So you're not allowed to use accumulators, for example. And I will not give you more than 50% of the credit for a problem if you do not solve it by structural recursion. I will write in very clear words on the exam that you must write structurally recursive code. Now, does everyone, okay, let's just do this song and dance. Everyone should be able to do the song and dance right now. What is the template for a structurally recursive list function taking a single parameter? Everyone should be able to recite this from memory. Go ahead.
Define func.
Sure, func. Single
Yes.
parameter,
LST.
then what?
And then cons.
Cond.
Yeah. Bracket, is it empty? Empty LST. And then something or other. Depends.
Yep.
And then the next line is else. Else,
And then,
parentheses,
yeah, I'll write it like this.
something or other, first list, then ellipsis, func restless, and
Yes.
ends it all.
Now closing that, then that closes. And then two more. Okay, it's nicer when you type it. Writing racket code by hand doesn't look so nice. And so what does structural recursion mean? Structural recursion means that you are not allowed to talk about lists in any way except by way of the first of the list and the func of the rest of the list. For example, you're not allowed to talk about the rest of the list. You're only allowed to talk about the func, the recursive value of the rest of the list. And that's the idea behind foldar, for example. So here in this structurally recursive template for a list, what are the three pieces of information? What do you need to do to complete this template? I mean, you need to do two things. What are they?
Like I said, sorry.
So you have here this case. You need to complete that. And here, let's call this the empty case. And then we can call this maybe the cons or inductive case. And in the inductive case, what are you saying? You're saying how to combine the information of what the first of the list is with the information on what the recursive call of the rest of the list is. Now, if you think about this, think about a function like sumList. So what happens in the empty list?
You output 0.
And then in the other case?
Else you sum the first list to sumless restless.
Mm-hmm.
Take some numbers.
So if you actually think about this, when you're combining these two things, you do not know anything about what the list is. When you look at the sum list of rest list, that's just a number. And then the first of the list is also a number. And from the knowledge of those two numbers, you can say what sum list of LST is. So you know what sum list of the rest of the list is, that's a number, and you know what the number is, the first of the list is, that's a number. And from those two numbers, you can say what sum list of list is. Now, the information that you had at your disposal was much less information than a list. A list is a very big object. Potentially, it has millions of items in it. But here, you're able to answer the question only by knowing two numbers. And that's the idea behind structural recursion. The reason that these two things are in the template is because that's the only way in which you can talk about lists. You can't talk about the second elements of the list. You can't talk about the rest of the list. You can only talk about these two blocks. And so, for example, if you think about how to combine these two pieces of information, if we call this piece of information, let's say X, and if we call this piece of information Y, then here, what you're really doing is you're taking plus XY, right? And so, for example, if you wrote a function that just did that, let's say a lambda that takes two parameters, X and Y, and it sums X and Y, and then you put that in a folder. So this is how you combine them. Then you say, what's the base case? Well, it's 0. And then I put list. And so that's sum list. But if you look at lambda xy plus xy, that's just the same thing as what? How do I rewrite this function?
Is plus?
Yes. Plus takes two arguments and returns the sum. So that's another way to write it. But you could also write it like this. So the entire idea behind foldr and higher order functions is that you're passing into the first argument for foldr a way of combining these two pieces of information. This is supposed to be some abstract function that combines the two pieces of information. Then 0 is just the results in the base case. And then you pass foldr a list. So foldr is nothing but a higher order function that captures, abstracts the abstraction of structural recursion. And I think the key insight in understanding foldr is that the sum list of the rest of the list has a lot less information than the list. Any questions about that?
Yeah, so suppose that I'm going to use a foldr, but I forget which order the arguments have to be in. So could I then look up the documentation of foldr?
Oh, it's in the homework problems. I give you the definition of foldr. And Prabhakar on his website has that as well. Okay, you know what? Prabhakar on his on the notes, he makes it so that the syntax, when he uses right syntax, it has links to the Racket documentation. So I may as well, fine. If you want to read the docs, you're allowed to. I will add as another allowed resource the Racket documentation, the official Racket documentation.
Thanks.
but this is helpful if you're used to reading about documentation. Most people are not familiar with reading documentation. And this is an official website. I'll send you a link to it. Single official website. However, this isn't so that encouraged because you're going to have to work with a very restricted set of features. So you shouldn't be looking up random functions. There's going to be a very small list of things that you can do, but sure. Anything else?
Just
where will the test be posted?
I'll email it to you.
Okay.
Just a quick question. So the two folder statements that are on the board right now, they are equivalent?
Yes. Because, for example, if you take the function lambda xy plus xy, and you evaluate it on two numbers like 2 and 3, then that becomes, in one step of reduction, it substitutes x and those values of x and y in the body. Well, that's the same thing as had you evaluated plus on 2 and 3, right?
Yes.
So in fact, this works for every single function. Every single function is equivalent to a lambda of its arguments followed by the function. And when I say equivalence, I mean computationally equivalence. Or rather, its behavior is undistinguishable. There's an extra reduction step, but its behavior on all inputs is the same as the original. Any other questions?
How many points will the bonus problems have?
Oh, not that many. Also, the exam doesn't have a denominator. The exam is not out of anything. Denominator. So in other words, there is a maximum score, and bonus problems will account for about 10% of the score. So it adds 10% to the max score. So it's going to be, let's say, about 10% of the max score. The last bonus problem is going to be worth, for example, 2 points, whereas one of the other problems is going to be worth 20. So the other bonus problems are going to be worth more, but the very last bonus problem is going to be purely for the sake of earning hacker cred. It's going to be very few points, but very satisfying to solve. And now when I say that the exam doesn't have a denominator, well, if the exam had a denominator, then you'd feel very bad if you, for example, scored 50% on it. Well, you're not scoring 50%. I'm fine with whatever scores people get. I have no idea where the target midterm is, but I expect a trimodal distribution. I don't expect a curve. There are going to be three very distinct groups of scores, and they're going to be spread apart. So if there was a denominator, I would expect that the average on this exam would be less than 50%. But there isn't a denominator.
question. So you will let us know how to submit each problem. For instance, if it's a
Yes.
proof, like use a text
It's going to
file
be on
and-
Marmoset. Everyone.
So submit all the pieces.
Yes, individually, but they're going to be labels. So 50% is a very respectable score on this exam, actually. But that's why I say that there isn't a denominator. Anything else? Well, I mean, for everyone, this is your last chance to ask theoretical questions. Does
Hey,
anyone
do you
want
think
Go ahead.
do you think when we finish the exam we could just email you random math questions until Wednesday?
Sure. I'm actually probably going to finally have a bit of free time because setting this up took much longer and speaking with people on the weekend took very long. Go ahead. Well, I mean, if it's not about
If it doesn't
the
pertain to
exam
the
and I'm
course.
convinced that you've
Yeah.
submitted, yes,
Yeah.
sure. That's fine.
I have a question about filter.
Yep.
Okay, so the examples that I've seen on filter makes sense. So when filter is consuming the list, that it looks at that particular element that it's at and compares it or does some computation on it. So the question is, can filter be used to invoke something or look at something externally, or that's just its purpose? Just
What does that mean?
I'm looking at that particular element and I can only do like basic stuff with it.
Well, you can run any, filter takes a predicate, right?
Yes.
So any function that returns a Boolean, and it evaluates that predicate on each element of the list.
Mm-hmm.
Well, that predicate can be whatever function you want to write, so long as it returns a Boolean. So I can give examples. So, okay, let's open a new tab. I'm going to stay in Racket. So let's say I want to check numbers whose square is bigger than 25. And then give me some list of numbers. Oh, by the way, this quote notation, it's available in beginning student with list abbreviations. So you are allowed to use quote notation on the exam, not quasi-quote, but quote. So you can write lists like this. I mean, well, you can, they'll be accepted by your program. I'll give you 3 release tokens on Marmoset for the entire exam. Okay, so is this an example of what you were asking about?
Yeah, so in this particular case, say I'm at 1, it's asking, so it's going to return a Boolean, either true or false. And if the square of say 1 is it greater than 25? No, it isn't. So I get false. So it's not going to be in the list. It only keeps elements that meet a criteria.
Right. Now, if I actually look at this list and I think about how would I build this list, it is most natural to write a list builder function for this using an unfoldr. That's like one of the really good things that unfoldr can do. So unfoldr doesn't exist in Racket. But I would write that list generation function as, wait, is that a homework problem? That might be a homework problem. Okay, I won't tell you how to write that list generation function with unfoldr. Any questions? Okay, next question.
Would it be possible to, you've done it in the past, but to provide this, how to test your own function? Was it check?
Well, so check expects.
Okay.
If you say, let's say filter, oh, well, okay, let's define that. So full Racket actually doesn't have check expects. So I'll switch to, let's say, beginning student. So I'm now switching to beginning student, and you'll notice that list notation is, oh, of course. Obviously, I don't have filter in beginning student. Whoops. It's not what I want. I want to run. Okay, so the test passed. However, you can also, you don't have to write text expect statements. You can just type it in the interactions window, right? You can just test it and see if it works, right?
Okay.
So check expect statements have the benefit that you don't have to remember to remove them before you submit. But you can also just test them in the interactions window. I mean, like, if you wanted to check that this function works, the most natural thing would be to just try running it on stuff, right? That's how you test.
Mm-hmm.
And like, there is zero excuse is if your code doesn't even pass the run button and you submit it. You should at least run your code on the input provided in the problem. That's the bare minimum, absolute minimum threshold of testing.
What's a good strategy
Okay.
for testing?
So I'm bad at writing tests. You should think about, well, I think the general strategy is think about all the things that could break your code and then try and cover different cases. You should actually look at your code and see what it does. And then, because if you look at the problem, it's not necessarily obvious in the problem what the different possibilities of input are, in the sense that this input causes your program to behave very differently from this input. That depends on the way that you've implemented your program.
Sure.
You can also look at your program and you can look at all of the places in which it will throw an error. So for example, if you're taking the first of something, then it's possible to throw an error if what you're giving it isn't a list. And so you can actually determine all of the points in which your program could fail. And then you could try and test whether those happen or not. And then the other thing that you should do is if your function, if it's not a function about numbers, but it's a function about something else, you should test it on non-number inputs. So for example, for unique left and unique right, you should have tests in which you test them on things with strings or lists. There isn't a very quick way to give an answer to what is the best way to test functions. You should do something that's convincing, and then your standard of what counts as convincing will increase with time, or become more refined in where you only need one or two pieces of information to be convinced. For example, I am convinced that this function works. I think I was almost convinced before I tested it, but I might have typed something wrong, but now I'm convinced. Any other questions?
Will grading be done on a curve, or is there a standard for the
Yes.
grade?
I expect people to get about 50% of the max score on this exam. There isn't a denominator.
Okay.
So don't worry about grades, worry about solving the problems. Oh, and so I think it sometimes becomes non-obvious, but academic honesty in a take-home exam is if the problems are hard, submitting an exam, for example, if you don't have the answers, which solves only 10% of the questions. When you're in such a situation where you have absolutely no idea what's going on and you're only getting about 10% of the answers, yes, it is academically honest to submit an exam in which you've only solved 10% of the questions. You're not in serious trouble if you do that. You are in serious trouble if you look up answers. And if you're already at the level where you're getting only very few questions, then you're not going to be intelligently able to get answers from the internet. Specifically, it's going to be very obvious to me. Very, very, very painfully obvious that you copied. Now, I expect no one to do this, but it is actually a logical point that you say, yes, of course, academic honesty. But when it comes down to the fact that, oh no, I've solved almost nothing on this exam, that's precisely where all of those sayings of, oh, well, academic honesty come in, because then you're in a pretty tricky ethical situation. But it's not tricky, you just don't. You submit an exam in which you've solved very little. That is the correct thing to do. Don't do otherwise. It's going to backfire terribly. So I answered that in response to, is the exam going to be graded on a curve? If you're really, really worried about the grade in a sense that you think that if I do this much on the exam, I'll certainly fail the class. Well, if you're trying, you won't fail the class. I will fail people who haven't submitted any homework and don't do things. If there's a level of class participation. But if you're participating and you're trying, yeah, you're going to get a decent grade. Well, for some definitions of decent. The valid definition of decent is the A's are the only decent grade, in which case there you're going to have to do something for an A, but I'm not going to fail people that try. Don't be tempted to copy something because you think that's the only way to pass the class. That's almost certainly going to backfire very spectacularly. Okay, any questions? Okay, so the exam starts in 3 hours. I'm going to do some setup last minute. And then I'm going to send it out. Also, not all of the questions are going to be on Marmoset at the start. Okay, good luck. See you on Wednesday.
See ya.
Yeah.
See you.
Bye.
Bye.